For decades, the Bermuda Triangle has swallowed ships and planes, sparking endless theories and fear. Now scientists have uncovered a shocking truth about the region.
There must be something there beyond science that's making this happen.
Their research shows that disasters there do not happen by chance. Powerful forces build long before catastrophe strikes.
This is an area prone to storms, to be fair.
It is an area prone to storms, but it's not a coincidence that all of this happened inside this concentrated area.
What once seemed mysterious is actually a warning. And understanding it reveals just how dangerous this stretch of ocean really is. The Bermuda crust. Before revealing the solved mystery of the Bermuda Triangle itself, let's first unveil what scientists have just discovered about the region. In late 2025, a study published in Geophysical Research Letters finally cracked a geological mystery that had puzzled researchers for decades. Using advanced seismic tomography, seismologists William Fraser of Carnegie Science and Jeffrey Park of Yale University analyzed data from nearly 400 earthquakes. Their analysis revealed a massive, dense structure deep beneath the Atlantic Ocean floor, a 20-kilometer thick layer of rock acting as a colossal raft, propping up the entire Bermuda archipelago.
This is really the only place that we can see this now up on dry land. The rest of it is all washed into the sea and is in a big layer.
This underplate is the primary reason the islands exist above water today, providing approximately 500 meters of buoyant uplift. The discovery fundamentally shifts our understanding of the region from a site of paranormal vanishings to one of profound geological fragility, holding critical implications for its future as sea levels rise. Bermuda's existence has always been an anomaly. Unlike volcanic island chains like Hawaii, which form over active, deep-rooted mantle plumes, Bermuda has shown no signs of volcanic activity for the past 30 million years. A separate, groundbreaking 2019 study examining a 2,600-foot-long rock core sample revealed its volcano originated uniquely. It formed from material hauled up from the mantle's transition zone, a deep, water-rich repository of ancient tectonic slabs left over from the breakup of the supercontinent Pangaea. This process created a volatile carbon dioxide-rich magma that erupted onto the sea floor around 33 million years ago, forming a volcanic pedestal. The volcanic foundation was just the beginning. As the extinct volcano cooled and subsided, a more delicate process took over. For millions of years, corals and other marine organisms grew atop the submerged platform. Their skeletal remains accumulated, forming vast limestone deposits. During past ice ages, when sea levels dropped, these deposits were exposed to wind and carved into dunes, which then fossilized into a porous rock called eolianite. This cycle created the islands we see today, a delicate, low-lying cap of permeable limestone and sand perched precariously atop an ancient, dormant volcano. The entire landmass is essentially a brittle, sponge-like structure. The 2025 seismic study answers why this fragile platform hasn't already sunk under its own weight. The newly mapped underplate, likely cooled magma that never erupted, acts as a permanent geological buoy. It is only about 1.5% less dense than the surrounding mantle, but on a scale of hundreds of kilometers, this slight difference provides the lift needed to maintain the Bermuda swell, an area of elevated seafloor. As co-author Jeffrey Park noted, this layer could support the bathymetric swell. However, this support system is static and finite. While it holds the crust aloft, it offers no protection to the soft, vulnerable carbonate islands above from the forces of erosion and rising seas. However, the immediate threat to Bermuda is not a sinking foundation, but a rising ocean. Data from the National Oceanic and Atmospheric Administration provides a clear, measured trend of increasing sea levels in the region. This relative sea level rise is the critical metric, combining increasing ocean volume with local geological subsidence or uplift. Fresh water on Bermuda does not come from rivers or lakes. It exists as those lenses compress, thin, and become saline. This is not a future scenario. Measurements taken over the last several decades show progressive saltwater intrusion across the islands. Wells that once produced drinkable water now fluctuate seasonally between fresh and brackish. During storm surges, seawater overtops the land and infiltrates the subsurface directly, bypassing natural filtration. Once salinity crosses a certain threshold, recovery is slow or impossible without artificial intervention. Sea level rise around Bermuda has been carefully tracked using tide gauges and satellite altimetry. The current rate is approximately 3 to 4 millimeters per year, slightly higher than the global average due to regional ocean circulation patterns. Since the mid-20th century, sea levels around the islands have risen by more than 20 centimeters. That number alone understates the problem. Each incremental rise increases wave energy at the shoreline, accelerates erosion, and expands the footprint of storm surge. Climate projections indicate that by mid-century, Bermuda could experience an additional 20 to 30 centimeters of rise under moderate emissions scenarios. By the end of the century, that number climbs towards 60 centimeters or more. For low-lying islands built on porous limestone, the difference between 40 and 60 centimeters is not cosmetic. It is existential. At that point, storm surge becomes chronic rather than episodic, and groundwater salinization becomes permanent. Inundation refers to temporary flooding, water covering land during storms or high tides. Land loss is more severe. It occurs when erosion, dissolution, and subsurface collapse permanently remove the island's physical structure. Bermuda is increasingly facing the latter. Coastal cliffs retreat as wave undercutting exploits fractures in the limestone. Sinkholes form inland as subterranean cavities enlarge and collapse. The infrastructure built decades ago assumed a stable water table that no longer exists. Researchers studying carbonate platforms warn that once a certain threshold is crossed, degradation accelerates non-linearly. Small increases in sea level produce disproportionately large impacts. Saltwater intrusion kills vegetation, which destabilizes soil. Soil loss exposes bedrock, which dissolves faster. Dissolution widens channels, allowing more seawater to flow inland. This feedback loop is already observable in parts of the islands. Unlike deltas or barrier islands, Bermuda cannot migrate. There is no sediment supply from rivers to rebuild beaches. There is no continental shelf behind it to retreat onto. The islands are fixed in place, anchored to a narrow volcanic core that offers no lateral escape. In geological terms, Bermuda is a stranded structure. What makes this especially significant is not just the vulnerability itself, but its visibility. Bermuda is not a remote atoll. It is a major tourist destination, a financial hub, and a symbol of permanence in the Atlantic. Cruise ships dock there daily. Resorts line its coasts. Airports, tunnels, and causeways connect land that was never meant to bear that load indefinitely. The very success of Bermuda as a destination increases stress on a system already nearing its limits. Today, tourists still flock to Bermuda's pink sands, largely unaware of the fragile geological wonder and the invisible freshwater crisis beneath their feet. But while modern science has demystified the geology of the islands, a more notorious and directly threatening phenomenon is brewing in those very seas, one driven by the same warming climate that threatens the island's existence. The Triangle of Death. In a landmark study for a Channel 5 documentary, oceanographer Simon Boxall of the University of Southampton harnessed advanced digital simulation to confront the Triangle's most enduring tragedy. By constructing a scale model of the USS Cyclops, a massive 590-foot-long Navy collier that vanished with 309 souls in March 1918, and subjecting it to simulated ocean conditions, his team isolated a definitive killer. The research demonstrated that so-called rogue waves, steep walls of water measuring in excess of 30 meters, could snap the vessel's long, flat hull in two, sending it to the bottom in less than 3 minutes. This compelling forensic evidence shifting the discourse from paranormal speculation to the concrete physics of extreme oceanography. The notion of the Bermuda Triangle as a supernatural zone is a purely modern invention, meticulously constructed through a chain of sloppy research and sensational repetition. The phrase itself was coined by author Vincent Gaddis in a 1964 article for Argosy magazine, a men's pulp publication. It was Charles Berlitz's 1974 bestseller, The Bermuda Triangle, however, that launched the myth into global consciousness. Berlitz, a linguist with a passion for the paranormal, filled his work with inaccuracies so profound that investigator Larry Kusha later noted, "If Berlitz were to report that a boat were red, the chance of it being some other color is almost a certainty." Kusha's seminal 1975 work, The Bermuda Triangle Mystery Solved, systematically dismantled the legend. He found that writers often failed to mention that disappearances occurred during powerful storms, reported on ships that sank nowhere near the triangle, or even chronicled vessels that never existed outside of imaginative prose. Authoritative institutions have also consistently rejected the triangle's alleged danger. The U.S. Coast Guard maintains that the combined forces of nature and human fallibility explain every incident, and they see no pattern of mysterious losses. The global insurance market, Lloyd's of London, confirms that they do not charge higher premiums for vessels transiting the area, as the loss statistics are unremarkable. A comprehensive 2013 study by the Worldwide Fund for Nature listing the world's most dangerous waters for shipping did not include the Bermuda Triangle. As Australian scientist Carl Kruselnicki has emphasized, the number of ships and planes that go missing in the Bermuda Triangle is the same as anywhere in the world on a percentage basis. The simplest explanation for the high absolute number of incidents is the sheer volume of traffic. An estimated 1/3 of all U.S. privately owned boats are located in the region, and it is a major corridor for commercial air and sea travel. The earliest strange event associated with the region comes from Christopher Columbus's log during his 1492 voyage. He recorded erratic compass readings and sightings of a mysterious light. These observations, often cited as the mystery's genesis, have straightforward scientific explanations. The compass anomaly is a classic case of navigational misunderstanding. A compass needle points to magnetic north, which is distinct from geographic north. The variance between them is called declination. The agonic line is the meridian along which magnetic north and true north align, meaning compass variation is 0. In Columbus's time, this agonic line was located in the eastern Atlantic. As he sailed west, his compass would have begun to show a discrepancy. Unaware of this natural phenomenon, he and his crew likely interpreted it as a malfunction. The agonic line is not static. It has drifted westward over centuries and now passes through the Gulf of Mexico, not the Bermuda Triangle. The U.S. Navy explicitly states that no unusual magnetic anomalies exist in the region today. Also, the strange lights witnessed by Columbus's crew were almost certainly St. Elmo's fire, a luminous plasma discharge caused by atmospheric electricity that gathers on masts, spars, and rigging during thunderstorms. For medieval sailors, it was a known, if awe-inspiring, natural spectacle. The rogue wave, once considered a myth as tall as the triangle itself, is now recognized by physical oceanographers as the primary culprit behind many sudden maritime catastrophes. These are not simply large waves in a storm, they are singular monstrous anomalies that can appear from a direction other than the prevailing sea state. Described by sailors as holes in the sea or sudden vertical walls of water, they can reach heights of 30 meters or more. A catastrophic convergence of geography and meteorology fuels their formation in the Bermuda Triangle. The region is a highway for powerful weather systems. Storms brewing in the tropics to the south can collide with extratropical systems descending from the north. Furthermore, the triangle is straddled by the Gulf Stream, a vast, warm, and powerful ocean current flowing northward from the Gulf of Mexico. When storm winds oppose the swift current of the Gulf Stream,